So hello, welcome. I was working on notes for day 17, and I found this super cool relationship between breadth first and depth first search. I thought folks would be interested in, but then, the more I started to kind of study it, I thought it was going to be kind of intense, and this is not like a core skill for everyone. So here is like an extra video. If you guys are interested in this, you could watch this. I'm hoping it should come in around like 10 or 15 minutes, this little mini lesson. And it's a slightly different view of BFS, DFS. So it will reinforce your understanding and also shows like, one of these kind of like elegant math things that these two algorithms are actually extremely similar. They're the same thing, but we can swap one piece for another. And in the process of doing this little mini lesson, we'll introduce ourselves to queues and stacks. These are helpful constructions you'll see later on when you study algorithms. But let's dive in here together. I really need this to be full screen. Let me see if I could do that. Please be full screen. F5, that's a good button. Okay, great. Here we are. So day 17 extra. Another view of BFS, DFS. And we'll show again that these are very similar constructions, but we'll swap in a queue for a stack when we go from one to the other. And we'll introduce what is a queue and a stack. So we'll start here with depth first search. You guys have seen this in class. But our goal, again, in each of these search methods is that we're trying to just order all the different nodes which are connected to some given starting node. And what's our approach? Well, we start here at A in depth first search, and we remember from class that we're trying to like follow edges as long as I can go in depth first search until I get stuck, and then I kind of have to back up. That was kind of maybe the class definition, a hand wavy one, a light definition. But here's our approach that will kind of look in this more like programming centric thing. We'll have this thing called a to-do list, I'll call it, and this particular to-do list I'm going to say is a stack. I'll give you the stack rules in just a moment. But here's how it works. I start with adding just my initial node A to the to-do list. And then here's my process. In every step that I take, I'm going to pull a node from the to-do list somehow, and I will visit it. And in visiting it, I'll add it to my visit list. And then I'm also going to add its unvisited neighbors. Oh, excuse me. Oh my gosh, we're jumping all around here. Forgive me, I don't normally present with a PDF. But we add those unvisited neighbors to the to-do list as well, right? So here we are starting. A is in my to-do list, and we've not visited anything. We've just kind of initialized that stack. And why do I, keep calling this thing a stack and not just a to-do list in general? Well, it has certain rules that make it a stack. That is, I'm going to be adding items on the right, and I'll also be removing items from the right every time. You guys will see me do that. So let's take a step here. So first step, I'm going to grab something off that stack and visit it, right? So I'm now visiting A, you can see in blue. And so I'll add that node to the visited list. And I'm going to add all of the neighbors of A to my to-do list, right? The stack in this way. And just like we said in class, I could add these in any order, and all of them are valid depth first searches. My goal, however, is to visit those like when all else is equal. If I have many depth first searches orderings that are valid, I'd like to pick the one that has alphabetical order first here, right? So that the next thing that I pull, I'd like to be alphabetically first off the stack. And if you guys look at the order that I put them in, G, E, B, it seems a little bit funny. You're like, isn't that backwards alphabetically? Yeah, it is backwards alphabetically, but remember my rules for the stack. I'm going to be taking items from the right side of this thing. So the next item off my stack is B here. And then the next one will be E, and then the next one will be G. And that's actually like the behavior I want, right? That's the alphabetical ordering. So let's grab that next one off the stack. Looks like we'll pull a B down. We'll visit that. And it seems like I've added some more things to my to-do list, right? What are the neighbors of B? Well, I have C and D and A, but I've already visited A, right? So D and C are the only unvisited neighbors. And so I want to push them on the stack. And again, I'm going to order them like unalphabetically. Is that a word? Counter alphabetically, right? So that I pull them off the stack alphabetically first, right? So that I'm going to pull off that C, that most rightward element first, which is important because C comes first in the alphabet. So now I'll pull that C off the stack, and you'll notice I don't actually add anything to the stack. Why is that? Well, take a look over here at the graph. C has no neighbors, so there's nothing to add to my to-do list. So then the next thing I'll do is I'll pull a D off the stack. And again, no neighbors. Now let's pull an E off the stack and visit it. And it has one neighbor, F. So that's rather easy. I just pop that thing in on the right. And this step is a little bit funny. When I visit F, I'll visit it and I pop its neighbor G onto the stack, right? And it feels a little funny that there's two G's on the stack. This kind of thing can happen from like a programming standpoint. The stack is allowed to have repeated nodes. Notice that they won't show up in this visited list twice. I'll show you why in just this next step or two here. But we pull that G off the stack, that rightwardmost element, right? And in this final step, I'm going to pull the last G, but here's this, like, it's this first little line. If some node that I'm pulling from my to-do list is unvisited, then I'll go ahead and do this thing. This G that has already been visited. So you pretty much just remove it from the stack and skip that step. And if you take a look, you'll notice that this is the DFS ordering as you would have gotten it from another method. But again, something that I like about this to kind of emphasize is that you could really see how the computer's keeping track of just where we are. Something else that is beautiful about this is that it is the exact same thing as BFS, but we're just going to swap our to-do list. So that previously in depth first, we were using a stack. Now we're going to use breadth first search, which uses a queue. And how's that work? Well, we're going to add the items on the right and take the items from the left. So this is like a normal queue, like you'd show up at a bank, right? You get in the back of the line and the teller is pulling people from the front of the line so that you kind of can't, is the typical thing when we line up to get served in most capacities. A stack, again, is different. That was like the first person who's in is the first person who's out, which would be a funny way for a bank to run, right? Because then the last person who got in line is the next person up. You could be there forever. But again, that's a stack that we did for depth first. Let's see how this queue works in a breadth first search. I've highlighted in pink the only differences from depth first search. I've changed nothing else about this slide except the different things in pink. Just the fact that it's a queue, and how's a queue different from a stack? I'm going to add the items on the right and pop them from the left. That is the person who's been in the queue the longest is the next one to be removed from the queue in some sense. But I'll start just the same way. I initialize the queue with the starting node, and here I go. I'm going to visit A as kind of my first step, and then pop all these items onto the queue, right? Or I push onto the queue. But B and E and G are all going to head onto the queue. And one of the challenges I have here is that I want to put them in the queue such that when I remove them, they should be removed in alphabetical order. So you'll notice that here I do add them in alphabetical order because I'm going to be taking from the left. B comes before E, comes before G. Okay, so that's fine here. This is the alphabetical ordering. So then I grab B is the next thing. I grab it off of my queue. And what are the neighbors of B? Well, C and D and A. Of course, I've already visited A. So just C and D need to be added to my to-do list. And again, I'll put them in now in alphabetical order so that when I remove them, they get removed in alphabetical order because I'm removing left to right here. And I go, one more. Now I'll visit E in my next step. Visiting E has one, new neighbor F, so that I add that in. Again, even though A is a neighbor of E, there's no need to add it in because it's already been visited. Then I visit G. It has one new neighbor F. And again, notice that it's kind of funny that F ends up showing up in the queue twice. As you guys saw before, this isn't a problem. I will not visit it twice because I kind of check for that a little bit later. But it's okay that the node shows up in the to-do list or the queue twice. Then I'm going to visit C. It has no neighbors, so nothing new to add to my queue. I'm going to visit D. No neighbors, nothing new to add. I'll visit F. And then the second time I try to pull F from the queue, well, it's already been visited. So I'll just remove it from the queue. Then if you take a look, this is the BFS ordering, right? Which is kind of cute that you could see that the two are like super similar. So I hope you enjoyed. I think this is a good resource if you're somebody who just wants to see this again, just to like really validate. It's like a very methodical way of doing it. As well, if you're trying to like program this thing, I think this queue versus stack idea is probably a little bit more fruitful than some of the stuff we did in class. Take care.